non-targeted attack we have already discussed. If you say that you want to design a adversarial sample which can be basically classified to a particular target, right. So, your samples basically if a human will basically verifies, so it looks like a real sample, maybe you have a images of cat and dogs, right. You say that you have a image of dog, right. As a human we can see that there is a dog in the image, but you have changed few pixel, you have added certain noise in the data in the image. So, human is able to say this is dog, but your model is saying cat. So, that is the problem here, targeted attack problem. So, you want that all the images that you are perturbing, they should be classified to a particular class, maybe cat, or in digit I said that must be classified as 0 or 1, or you can say 4 or 5. So, this is called targeted and non-targeted attack. So, non-targeted means it can be classified to any one of the class, but not the actual one. Sorry. So, this is the adversarial approach here. So, you have adversary here which basically try to corrupt the samples. You have a training data set, you have a test data set module basically comes during the real time establishment when you have deployed your model. You have AI model and you have prediction here and you have to get the probabilities here. So, idea is basically your idea is for the adversarial approaches to get the wrong predictions. So, whatever model is saying, so you have a model that ML as a service as a black box setting, but we want to design a sample such that your model is not capable of doing the correct prediction. So, this is one of the toy example I am just showing here. So, let you have a linear classifier, basically this logistic regression classifier where it has a basically non-linear boundary. So, sigmoid we have. So, you just see here, so this is the model. So, probability that it basically assigns the sample y equal to 1, you can say labeled as 1 or you can say class 1 given the parameters is defined by this one, right, W transpose x plus b. So, this is the model, and you know that sigma is sigmoid represents the sigmoid function, you can say sigma of g is 1 upon 1 plus 8 power g. So, this is a bell, you can say that this is a function S shaped, right, and ranges from 0 to 1. So, the minimum value that it can have it is basically when g is in minus infinite, your input is minus infinite or very close to negative, very large negative value. So, this function has a value 0, and if you have a large value for large positive value, so g is positive, its value is near 1. Right. So, its shape is like S, right. So, that you have, so you can say rotated 180 degree or mirror image of S, right. Or you can say this is shape S shape or many times we call it bell shape and many. So, we generally use to basically map any number that are the values, the vector that you have to follow the probability or probability considerations, or you can say just map the data into the range of 0 to 1 smoothly. So, this is the logistic regression classifier hypothesis is this one. The simple logistic regression basically you can say a perceptron model. So, this is basically neuron, one of the neuron with sigmoid activation decides the class of the input x is 1 if h of x is greater than 0.5. If the sigmoid value whatever W transpose x plus b have found, so if the value is the sigmoid value, if you pass that value to the sigmoid and value you have greater than 0.5, it is class 1, otherwise it is class 0. So, it means that if you have a value equal to 0.5 or less than 0.5, it is classified as 0. So, for class 1 you have this one, let your data is this, you can learn it. So, maybe in today's session you just practice, you just code it and you just practice it. So, we have a sample here, you can see the sample. So, what is the sample? The input is 2, -1, 3, -2. So, this is the x, w is, we have designed the weight right now in order to just demonstrate it and bias b equal to 0. So, before the adversarial attack, so you just compute this value w transpose x plus b. So, how will you compute? You just multiply the corresponding values. So, x is a vector, so it is a feature vector, by the way, you can say. So, x is a sample, single sample, right. So, how many elements are there in that? You can see you have 10 elements, right. So, this is a 10 dimensional 10 feature input sample, you have 10 feature values, you have a corresponding weights, corresponding dimensional parameters, corresponding dimensions. Bias is 0, we are intentionally kept it, it might be, you might put certain value. So, if you compute it, you will see that you will get the probability that you will get is this one, 0.0474. So, probability of class 1 is computed as this. It means that it is not in class 1, it might be the other class, right. So, it is it belongs to negative class right now, because it is not class 1, because probability is not less than or equal to 0.5. But what we are doing, so we are adding, so every sample that we are getting, so what we are adding, so whatever weight you have, you just half the weight and add to the sample. So, your samples becomes, adversarial samples becomes 1.5, minus 1.5, 3.5, minus 2.5 and this. And now what you do, you just compute it, the probability becomes 88%. So, with 88% it is saying that it belongs to class 1. Actually, it is not a member of class 1 originally, but we have added certain things. So, whatever weight we have, we are saying that in the sample you just add that weight and then classify. So, some noise we have added. So, this is the idea behind the adversarial sample. So, given a sample, if you have access to the sample, try to basically perturb the sample, try to fuse certain, change the features, change the values in the image such that it belongs to different class. Right. And this can be done in with many ways, right. So, in black box setting, white box setting, whatever you say, right. So, attack spaces we have already discussed. So, now we are moving ahead towards the neural network based model. So, we generally try to exploit neural network models, right. You might have many models, you can perform attack on any of the model, it is not limited to this model only, neural network based model, but because these models are very popular and everyone is interested how these models works. So, that is why we have designed lot of attacks on this model only, neural network models, right. So, mathematically now we are representing the learning process. Just see here. So, you have a d dimensional input. So, you have an input with d dimensions, you have a feature. How many features you have in the data? D features here in this case. So, 10 is that example, right. So, now we are representing the generic representation. So, your input sample xi, ith sample has a d values, is a vector of d elements. You can say your data has d features. You might have a many such samples, it might be image, you can say here, it might be a stack of images, it might be many text samples, right, text data sample, it might be audio samples, might be anything. Corresponding labels are there, you can say for every sample that label is associated. So, it means your data is supervised. Right. So, you fed these two things to your model, this is the neural network model, and mathematically we call it let h theta, and I think you know the h hypothesis, right, we discussed, and h is the model in that hypothesis class. So, h is the member. So, let h theta is the model, theta is a parameter list, all the parameters that you have in that model. So, whether learning parameters or hyperparameters, whatever you say, so all the parameters set is basically theta, you can say. And then you have corresponding loss function. Loss function is basically you have a ground truth, you can say yi, the label that you have. So, every sample has true label, you can say yi, that is there, and the predicted value, that is you can say your model is giving you, so s theta xi. So, s theta is a model, when you give xi as input, it will give you the output. You can call it yi cap or you can say s theta xi. So, loss is computed using these two, ground truth and the predicted value. Now, what happens? So, this is the forward pass. So, you have xi, s theta might be a function. In the forward pass, in the you can say forward direction, you can compute this value s theta xi. So, this module will provide the value s theta xi. So, h theta xi you will get. Now, the thing is that we want to update the parameters. So, during the learning process, we have to compute the gradient, because you have to apply the gradient descent algorithm, gradient descent based approaches. So, you have to compute the gradient of loss with respect to basically parameters. So, how will you do it? So, we generally follow the chain rule. I think everyone knows the chain rule, right. So, how many whatever dependent variables you have right in the model, you just multiply them. You just split your computation in parts and then apply the chain rule, right, to compute the gradient, and that is the story behind the computation graph. So, if you are able to represent your computation as a computation graph, then getting this gradient is very easy. Computing gradient is very easy. The chain rule is basically pictorially represented, right. So, you can visualize that thing, and you can do basically compute the gradients correctly. Maybe we can show you that how can you compute it. So, any complex model, if you are able to represent it as a computation graph, you can very easily compute the gradient, right. So, here starting gradient of loss function with respect to the loss is 1 always, you know that. So, gradient of a variable with respect to the same variable is 1. So, that is here. Then we have to compute gradient of this loss function with respect to theta. Theta is a parameter, right. And then you can say you can compute the gradient of loss function, because these are the inputs. So, theta, in order to compute this s theta, you have xi as the input, you have yi as input, you have theta as input. See, theta is just a parameter, right. So, with respect to every input that you have in this module, in this block, you have to compute the gradient, because these are the inputs. And you know that what it signifies, what gradient basically signifies. So, gradient says that about the change, right. So, here if I say that gradient of this loss function with respect to theta, you can say set of parameter. So, it says that if you change, you put a small change in the theta. So, how much, what is the relationship, or you can say how much this L varies, right, this loss varies. If you put a small change in the theta, how this loss function basically affects, or you can say works are basically updated or changed. So, if you see the large change, if you put a small change in theta and you say that okay, there is a huge change in the loss value, then it means that gradient is high, right. So, that value is significant. If you say that if you change little, you just put a little change in the theta and loss is not basically, you are not able to affect the loss value much. So, it means that that parameter is not very sensitive towards the gradient computation. So, that is why you can say that gradient basically defines that how much, how sensitive your input is, right. So, for example, if you have a linear functions, you have a quadratic functions, cubic functions, you know that gradient accordingly gradient changes, right. If you have higher degree functions, gradient will be of will be a huge change in the gradient, right. Then you have to compute gradient with respect to input xi, maybe you can get gradient with respect to yi, whatever you want. So, suppose I say that you have xi as the input vector, d-dimensional input vector, and somehow we computed the gradient of loss function with respect to xi. So, what will it signifies? What will it signify? It says that if you change a little bit in xi, very small change you just do in xi epsilon. So, how much change you will see in loss function, loss value? So, xi is a vector, loss function is a scalar. So, if you compute this gradient, so you will get a vector value. So, what will you get? So, with respect to every dimension, every component of this xi, right, every feature value that you have in xi. So, how much change it basically incur to the loss, right, that will you get. Is it clear or not? Maybe I can just use the board. I think this concept must be clear to everyone. Okay, we have to go to whiteboard, right? Okay, can you? Okay, so we can choose a blue color. Okay, good. So, what I am saying that you have a vector xi. I think this side. Okay. So, you have xi, right. So, xi in d dimension space. So, what is this xi? Maybe I am just writing xi as a vector like this. So, xi1, so in superscript we have the feature id let. So, there is a first feature value for is sample, first feature value. Then you have xi2, this is the second feature value, this is not the square. This is let xi cube, third feature value, and likewise you have xi d. Maybe in between you have somewhere xij. So, this is your xi, right. So, this is a vector of d elements, right. You can say d cross 1. And let loss function yi is that we have for time being. So, yi is just a scalar, and h theta xi you can call it let yi cap, and this is again of course will be a scalar. This will have the same size, same length. It might be of any dimension. I am just assuming this is just for timing scalar. And let your loss function is just a squared error, loss of this yi and this yi cap is, let just yi minus this yi cap is square. Clear? So, what is the gradient of this loss? Maybe I can change the color. Okay, red color. Okay. So, gradient of this loss with respect to loss, it will be 1. How will you compute gradient of this? Okay, इधर से दिखाएगा. Gradient of this loss with respect to yi cap. You know the function, it is yi minus y cap square. So, how will you get it? You will see. Change the variable, right? So, you can say let this is pi. So, you have to compute the loss with respect to this pi. So, this loss becomes, if it is pi, you are assuming, so pi square, right, into gradient of this pi with respect to yi cap. Is it clear? So, this is chain rule. If you know gradient computation, you can do it directly, but this is a chain rule you can see here. So, what is this pi? So, this is this loss is basically pi square, right? Pi square. So, what is the gradient of this pi square with respect to pi? 2 pi. Then what is the gradient of this pi with respect to yi cap? So, this is assume this other variable is constant, is not changing by the way, not worrying. So, it will be simply minus 1, right. So, you will get minus, you can get 2 pi from here and minus 1 from here, you just multiply. So, it is minus 2 pi and pi, you know that what is this pi. So, this gradient is simply minus 2 yi minus y cap. So, this is called basically a squared error. So, if you have n number of samples, you just sum this, just take the average of all squared errors, we call it mean squared error. So, that is a very important loss function we use for regression problems, mean squared error. So, you can say that for n samples, this loss will be computed like this. You have 1 by let n number of samples I going from 1 to n, this yi minus this yi cap square. So, if you have n number of samples, we try to minimize this loss function. Okay. And what is this yi cap? yi cap is theta xi and h theta is your model. Theta is the parameters. Is it clear to everyone? So, now you can say here, so yi and yi cap are vectors. You can say that might be vector, but their loss function we are computing it is scalar. Okay. So, if you compute the loss with respect to this xi, let I am just writing here h theta equal to, just very simple one, linear model I am assuming for timing. So, let it, this is w transpose xi plus p, this is h theta. Then we can do for the sigmoid as well, do not worry. S theta is w transpose xi plus b. So, how will you compute the gradient of S theta with respect to xi? You will get w, right? That vector you will get. Now, the question is, you have to compute gradient of this loss function with respect to xi. So, how will it be represented? So, with respect to xi, it's simply xi because it's d dimension vector. So, the output that you will get is gradient of loss with respect to first element. Is it clear? Xi is a vector, so you will get L, you can say loss function is a scalar, so you will get your output will be of the same length, right, vector length. Let you have a two vectors, let I am just writing here, you have a q vector, let qi is let d2 dimensional, let d1 for timing, and let you have another vector Ri, which is let d2 dimension, and if you want to compute gradient of this Qi with respect to this Ri, what will you get? So you will get a matrix, right? Because gradient is computed with respect to every pair of component that you have in this relation. So for every component of xi, or you can say you have to compute the gradient of for every component of xi with respect to every component of I. For every component of xi, you can say qi. So for every component of qi, let qi I am just writing 1. You have to compute gradient with respect to every component of I. So likewise, you will have for qi1, qi2, qi3 up to qid d1, and then row wise you can say that you can take the transpose as well, it does not matter much for timing. So this is qi1, second value will be ri2, right. So it is ri2 for second row is for second component of the denominator that you have. So that's the ratio of change, right. So that's why people call it this del qi, del ri. So these are the small changes, because you know that how this is defined, right. So it is basically if you have a function, any L function, you can say this loss. So how much change if your input is xi, if you put epsilon here minus L of x, you just epsilon is a very small quantity, positive quantity, right. You just see that divided by 2 epsilon, just make the limit epsilon tends to 0. So this defines the gradient, right, if you remember. So what is this? So this is d Li dx. So this is a because very basic math, right. So you know that how can you compute the so what it says that, so basically maybe denominator I can just write in a different way. Otherwise you will not be able to understand. Maybe okay, this color is okay. So this is x I plus epsilon minus xi minus epsilon. Okay. Now is it clear? So denominator is basically change in the input. So what is the change? So change is of 2 epsilon. So corresponding to this change, how much change you basically sense in the output or in the function L, right. So this ratio basically defines the gradient, or this ratio defines the derivative. So this is rate of change, right. So and you have studied in school as well, right. So the function of velocity. So velocity, what is the velocity? Velocity is the change, rate of the change in the distance with respect to time. What is acceleration? Rate of change in velocity with respect to time. So higher order, right. So the same thing is here, rate of change in loss function with respect to the change in input. So this defines that how sensitive your input is. So for example, here you have this, you have a loss function, you have a features. This is the first feature, this is the second feature, this is the dth feature. You just see the change. Given an input, you just see the change in the loss function. So all of these will have different values. You just see that which one has the maximal change. Change might be positive, change might be negative, right. So what is the maximal change here? So suppose you say that okay, some jth feature has changed. So let you have a xij somewhere. So this basically gradient of this loss with respect to this one, and let this has the large change. So, it means that if you change something in this, right, if you put a little change in the jth feature, somehow jth feature is corrupted, so your decision might change, right, because it will affect more to the model, right, during the learning process. So, that is the idea. So, we try to find out the features which has basically large changes. So, most of the algorithms that we will discuss today. So, fast gradient sign method, you just compute the gradient, change the sign, right. So, if you are doing minimization, it acts to it's inherently, you can say mathematically, it says that if your model is saying that you have to move in the negative direction, you say that no, I will move to the positive direction. We just change the sense, right. So, if the class is classified as positive, because we have reversed the sign, it becomes negative. Another method basically are there. So, we say that okay, you just put very simple, or you can say a small change, you just change the sign, get the sign of the gradient, and just based on the gradient sign, only the sign, whether it is positive or negative, just try to add some noise, positive or negative noise values, try to perturb the samples. We call it fast gradient sign method, FGSM. So, we will discuss today, and there are other methods what they do. So, they starting adding certain noise till the model tries to decide for some incorrect predictions, right. So, we call it basic iterative method, or you can say projected gradient method. So, we have that in today's session, and we will demonstrate maybe after the lunch session, and maybe we will give certain idea about the generative adversarial neural network, right, and we can discuss tomorrow. So, can you see here? So, this is clear to everyone. So, by the way, this matrix is called Jacobian, right. If you are computing the gradient of a tensor with respect to tensor, it is called Jacobian. Okay. Maybe one more thing I can just tell you here. So, so that what is the time, by the way? So, 11:40. Great. Okay, good. No worries. So, can we move it? Can we get new page? So, is there any way to get? Second one. Will it be saved? Yes. So, I am just going to discuss the computation graph, maybe 10-15 minutes will take more today, right. Maybe in demonstration we will try to cover few things, do not worry, because the basic idea I want to give you, otherwise you will not be able to implement, right. So, we will discuss the computation graph here. Right. So, suppose you have a function f of, let you have two variables xi1 plus xi1 and xi2. Now, you know that what is xi1. So, xi1 is one variable and xi2 is another variable, and your output is simply xi1 plus xi2. So, how will you compute gradient with respect to xi1 with respect to xi2? You know that this is addition operation and you can directly get 1. So, you know that how can you compute it. So, this is with respect to xi1, you know 1, and with respect to second component it is 1, because you have addition operation, and this is not a square, by the way, please note down. Otherwise, you can say xy, if you want we can put that, maybe I can put that, otherwise it will confuse you. Let f of x plus y. x comma y is x plus y. You know that gradient of this f with respect to x is 1, gradient of this f with respect to y is 1. So, how can you visualize this computation as a computation graph? The idea is, you just whatever operator you have here, just make a node. So, we have a node here. So, we have to perform the plus operation. We have x as input, we have y as input, and we have output this f, and this is x plus y. How the gradient is computed? How this derivative is computed? So, we will basically follow this backward direction. So, gradient of f with respect to f will be 1. And for addition operation, you know that if you have addition operation and if want to compute the gradient with respect to the input, it is 1. So, we have not to do anything. So, this 1 you can say backward direction, you can say gradient of this f, that output with respect to this input x is 1, and gradient of here with is again 1, you can say gradient of this f with respect to y is 1. So, how will you compute the gradient of this f with respect to basically this y? You can say you multiply it, you can get it, right. Suppose I say that your function is, maybe I can just change another menu, new page. Now, I am just going to take little complex function. Let you have, f of x and y. Let it is x plus log of y. How will you compute the gradient with respect to x and y? So, how can you compute it basically in the form of computation graph? So, now you have two operators, right. So, you have a plus operator. So, you have a log operator, you just give input here to the log function, it will give you output, and that output will go as input here. This x is input to this module here, you will get f here, and f is you can say x plus whatever is in the log y. Is it clear? So, how will you compute the gradient? So, gradient of this function f with respect to f. So, very simple step we are following. With respect to every operator, this is plus operator, just put 1. With respect to this operator, this is 1. What about this one? So, what is the derivative of log of x with respect to x, right? So, if you compute the gradient with x, it is 1 by x, right? So, here whatever input you have, so it is inverted, right. So, it is simply 1 by y, 1 by y. So, if we want to compute the gradient of this output with respect to this parameter, this variable, we just say that okay, whatever comes on the path, right. So, whatever gradient comes on this path, we just multiply all the values. So, what is the gradient of this f? Sorry, can change the color. So, this gradient of f with respect to this y is you just multiply all the gradients. So, this is 1, you have 1 right here, 1 into basically 1 into 1 by y. So, it is 1 into 1 into 1 by y, it is 1 by y. Is it clear? And what about this gradient of this with respect, sorry, this one you can say for this, you can say 1 into 1, that is 1. Now, just going to little more complex one. Okay. So, let your function f of let you have single variable x is 1 upon 1 plus e to the power minus x. This is a sigmoid function, right? And you can plot it like this, right? So, that we discuss in the sigmoid logistic regression, right? You have this function. here it is you can say plus 1 and this is you can say plus infinite and this is minus infinite. So, this is the function you can plot it. So, how will you represent the computation graph for this one? Tell me. So, exponent is a operator, right? Addition is a operator. You can put a negative symbol. You can multiply with minus 1 whatever you want. So, you can expand it into this one. Okay. So, by the way, can you anyone tell what is the gradient of inverse what is the gradient of x with for 1 by x? You know that this is minus 1 by x square, right? So, if you have an inverse operator, so what it does? So, inverse operator basically if you compute the gradient, so it is simply the negative of 1 by input square. So, that is the idea. So, we will do it here. So, x is the input, we have a multiplier here, this is a multiplication symbol. So, suppose you have a f of x into y, let f of x y is x into y. So, you know that what is f of x, sorry gradient of f with respect to x, it is y, right. So, gradient of f with respect to x is y and gradient of f with respect to y is x. So, they simply exchange of variables, exchange of input. Multiplication operator do the exchange of inputs, just addition operator just 1. So, many things you can remember directly. Then I will tell you the story how the modern packages like TensorFlow and PyTorch. So, they use this strategy to compute a very complex gradient for very complex neural network. Multiply with minus 1. I do not put this circle here. So, now you have minus of x, just compute, provide the exponent operator here, you will get e power you will get e to power minus x here. Now, you have addition operator here, just add addition, you have to add with 1, then whatever you have got you just provide the inverse operator, right, and you will get your f. Is it clear? So, just see here what is what are the sub component here. So, this will give you let I am just writing let this is p q r, okay, let this is p and the output that you are getting is p and p equal to what is this minus of x, right. What you are getting here? So, here you are getting e to the power minus x, right. So, let this is q for time being. This is addition operator, right. So, what will you get here? So, you will get this 1 plus q, right, 1 plus e power minus x, you can call it let this is r and this is you can say 1 plus e power minus x, or you can say 1 plus q. So, I am just giving this something to you just in order to understand, and then you just have an inverse operator and this f you have, and this is this operator says that 1 by whatever input you are getting. So, this is r, right. Is it clear? This is r, by the way. R you can say 1 by 1 plus e power minus. So, can you see this computation? Now, can you compute the gradient with respect to x, gradient of f with respect to x? Just see. You know the basically local gradients for every operator that you have here. Maybe I can choose the color red. So, this you know that what is this 1 gradient, sorry, change the color. Which color should I choose? Okay. So, this is you know that gradient of f with respect to f is 1. What about this gradient? Minus 1 by input square, right, r square. What about this? 1, what about this? 1. When it is constant, so it is not required, so you have that will be simply 0, you can say, it is not required, by the way. So, what about this? So, you have a, you can say what is the gradient of e power x with respect to x? It is e power x. There is no change. So, whatever input you are giving here, what is the input? P, and what is the output? output is q, right? So this gradient is simply q, right? So whatever function you have, so that is the output, right? E power x, power x. So this is q. What about this? Constant, so you can say 0. It is not going to change or vary. So what about this? This is a multiplication operator. So for multiplication operator, you have to exchange the input. So what is this? So it is -1. So can you compute the gradient now? So gradient of this f with respect to x is, just tell me, multiply from that one. So this is the path, right? This is the path we are following. You just see. So on this path, whatever gradient, local gradient you computed, you just multiply. Multiply. Below 1, maybe I can change. 1 into -1 by r square into addition operator 1, right? You just see 1 into q into -1. So just put these values. This is q by r square. What is q? E power minus x. What is r? Right. And you can write it simply. I am just writing it just for another purpose. You can write it 1 upon 1 plus e power minus x into 1 minus 1 upon 1 plus e power minus x. Both are equivalent. You just check it. So inside what will you get? So it will be e power minus x divided by 1 plus e power minus x. If you multiply with it, you will get this one, right? And this is the sigmoid itself. You can say this function fx, and this is 1 minus f of x. That's why the gradient of sigmoid function is, you have not to compute anything. If you have computed the function, if you know fx, you want to compute the gradient value, how will you get? Sir, fx into 1 minus fx. So in the forward pass, of course, you have to compute it when you are doing this operation. You have to compute this value f. But when we want to compute gradient with respect to this parameter, so we have direct function. You can directly compute the gradient without worrying. So that's the beauty of the activation functions. So whatever activation function we want to design, so they must be very quick in gradient computation and should be written in terms of the function itself most of the time. So like tan h you can write. So what about the tan h? So if you have a function tan h, let f of x is equal to tan h. Right, so tan h of x. So what is the gradient? You know that 1 minus tan h square, right? And that you can represent with this using the sigmoid as well. And only the thing is the difference here you can get is this, right? So this function tan h, so this is tan h, this was sigmoid x, you can call it. And this ranges from -1 to +1. We'll discuss when we discuss about the vanishing gradient, exploding gradient, maybe sometime. So, but you have a sigmoid function. Can you see here fx into 1 minus fx, and you know that all the values for fx will be in the range of 0 to 1, right? So whatever value you get, it will be in the 0 to 1. The maximum value you can get is 1. Minimum value for sigmoid you will get 0. So you can say this one, right? Only the values output you will get in this. Right. So if you compute, if your fx is let 0.5. So where is it 0.5? So when this x equal to 0, right? Your input is 0, you have a 0.5. Right? This is 0.5. So if your gradient is 0.5, sorry, your function value is 0.5 at particular point, maybe here it is 0, so x equal to 0. So what will the value of the gradient at this x equal to 0? Fx, you know what is the value of fx at x equal to 0? You can put in the equation, you know that 1 upon 1 plus e to the power minus 0. So e power 0 is 1, so 1 upon 2, it is 0.5. So what will the value of gradient? So 1 by 2 into 1 minus 1 by 2, it is 1 by 4. So at 0, gradient will have 0.25 value. Likewise, you can compute it. So just say because this function is fx into 1 minus fx, if fx is smaller, 1 minus fx is going to be higher. If 1 minus fx is larger, fx is going to be smaller. So what will the maximum value of the gradient? What will be the maximum value of the gradient? The maximum value that from this function you can get. Let you have a value x and x into 1 minus x. So what will the maximum value you can get? And x is between 0 to 1. Maximum value is 0.25, half into half, right? And other values you will always get below than that. So that's why if you plot this function, this whole, so it is like well safe, right? And this is by the way 0.25. So just take the sigmoid and try to maybe compute the gradient, plot it, you will see this. So we will see that many values for many, so only this region you have certain things, otherwise you will either have 0 or you have so in both the sides you have 0. So in neural network, if you have many layers, you have huge sigmoid activation. So many values during the gradient computation we are multiplying. So those values are basically following this particular space, this place, and they are near 0. They are near 0. So once your gradient is near 0, so what will happen? You know that the stopping criteria in optimization process. If your gradient is near 0 or very small, so learning will stop. So this problem is called vanishing gradient problem, right? So vanishing gradient problem, this is basically due to the multiplication of very low values during the gradient computation. So that's a vanishing gradient. So gradient basically vanishes. Another one is if you apply other activation functions like ReLU and others, there might be a chance of exploding gradient. If values are multiplying maybe in linear activation, so it might be very huge, right? So for gradient, exploding gradient, we have a very standard trick, we call it clipping. You just clip it. Just whenever it is going out of the bound, right, out of the certain decided range, you just clip it to the maximum value that you want or minimum value that you want. But vanishing gradient is dangerous, right? So for this we have a different type of neural networks like residual networks. So what you do? So in the neural network you just sort the connections. So for example here, just see this one. Suppose I sort this connection from here to here, right? Let I am just giving the idea. Let I am just giving this input, this P, right? Input to this inverse as well. So now when you do the backward pass, compute the gradient, so you have to compute the gradient with respect to this variable as well, local gradient. Is it clear? So gradient will flow in both the directions. It will go here also and here also. And once you compute the gradient at this point, because it is you have two places, so gradient will come here as well. So gradient will be added. So this is like water flow, right, in the pipe. Right. You say that okay, forward pass is just flowing the water from inlet to outlet, backward pass is flowing the gradient from outlet to inlet. You just reverse the process. You just send back water to the inlet, right? And many times you know that that is sending basically water from outlet to inlet is might be costly many times if their altitudes are different, right. So the similar thing is here, computing gradient is little heavier than the just forward pass. So you just represent your computation, your whole model, right, whole computation in this representation. We call it computation graph. What we call it? Computation graph. And TensorFlow, PyTorch, both the libraries basically uses this representation to compute the gradient. So they know the gradient, local gradient of these operators like multiplication, addition, subtraction, inverse, exponent, logarithmic. So all the basic operations that you have. So you have, you just write a function for these, and whenever you have a complex function, you just represent them in these modules and just multiply the local gradients, right. Even you can get the code also for converting the neural network, or you can say any computation into computation graph, and they have visualization tool as well. So TensorBoard, even TensorFlow you can use to visualize the whole computation, right. Okay, so maybe I think this is okay for all of you, right. So suppose I say that we have a neural network, just see one neural network I am just giving you, just tell me the gradient. So let your model is S theta, xi is 1 upon 1 plus e to the power minus w transpose xi plus b. Can you represent this computation as a computation graph? And we have a function, loss function L. Maybe I can change the color. It is going to little dense. Your loss function L is simply yi h theta xi equal to yi minus h theta xi square. Now you have to, you just tell me that what is the gradient of this loss with respect to this theta. Sorry, instead of w you just write it theta. Sorry, this is theta. Please note down this is theta. This theta, and let this b is not there. What I mean, because b is embedded in this. Okay, this only theta transpose xi. So this is loss, and just can you tell me the gradient of this with respect to theta? So what is that value? Just tell me. I am drawing a box here so that it should not go out. Just design the computation graph quickly. You will follow the same step here that you have made here, right. So only the thing is that here we are, so you have to multiply with -1, so one step back you have to come. Just what you add here, you just say that you just have a multiplication operator and you have two inputs, right. So you just say that you just add here. So I am just saying that you have a operator here, this is multiplication of, maybe I can change the color. So this is a multiplication operator. Here you can say xi is the input and theta is the input. Is it clear? So theta and xi. Now just this component we have added, and this f becomes L now. This is now L, right? And you just say that okay, this output that you are getting here, you just let for timing you just call it z. Right? As z equal to just theta transpose xi. So this is just theta transpose xi, nothing else, and all are same. Can you compute it? So you know till that point you know what is the local gradient here? So exchange, right? Theta. What is local gradient here? So you can compute with respect to theta, it is xi. Multiplication operator is there, right? Just you know that what is till that point you know what is gradient of L with respect to g. You know that minus q by r square. So plus q by r square, right? Now you have to multiply with this theta, right. So, that is very simple one. So, q by r square that you have multiplied by one more component you have to add. What is that? So, this is not L, by the way. So, this is your h theta. So, this is h theta you have got here. You have to add one more unit. So, where you have this loss function, you just put yi, you have s theta from here, and you will get output, right. And what is the basic gradient of this loss function with respect to s theta? So, it is minus 2 into yi minus s theta. So, so just write it, maybe I am writing in more elegant way. Just say minus 2 into yi minus h theta xi into this component q by r square into xi. That is the gradient. Is it clear? So, this is logistic regression, right. Gradient of logistic regression, or you can say single perceptron model in neural network, single neuron that you have in the neural network. So, likewise you have many neurons. So, every neuron you will get the same component, just put in the vector, you will, right, your task is done. So, in the maybe I think time is up, right. So, okay. So, we will discuss more maybe in the next session. So, we will do some hands on and we will keep on flashing the slides also, right. So, is it clear to everyone? So, given any neural network, any even not neural network, so any function you can compute the gradient. So, we will show you the neural network and we will show you that how can you compute the gradient. Maybe I can just give you the idea here only. Just wait for 2 minutes, just 2 minutes. Okay, new base. So, single hidden layer neural network I am just giving, and just giving you the loss function and all the gradients. You have neurons here. These are the neurons. Every neuron is the logistic regression in some sense, you can say, with different activations, by the way. Let you have 2 dimensional input, xi1 and you have xi2. So, 2 dimensional input. This is, I am just considering dense layered neural network. Every neuron has a bias. So, W transpose xi plus b. So, every neuron has a b. So, this neuron has, I am just now defining the layer, let this layer ID is 1. And every neuron we are representing using a small n. So, this is this is n1. So, superscript in square bracket let it is layer ID, and this is the first neuron. This is similarly this is the second neuron, superscript is the layer ID. Likewise, let you have p neurons, right. So, this is simply np first layer. Is it clear? You have single output here, single neuron in the output, you can say. So, this is layer 2, you can say. So, this neuron can be represented as n1. Is it clear? So, थोड़ा सा time हो रहा है, just finish कर रहा हूँ, right. And this is the output that you are getting here. Let you can call it what I mean yi cap. Then of course you have a loss module here. So, loss function is saying that yi minus. Okay. So, you have a minus operator here. You have at this yi, you will get yi minus yi cap or yi cap minus yi. So, whatever operation you want to define here, let us say this is yi cap minus yi, right. Then you have a square operator. So, and this is your loss. Is it clear? Okay. So, this is our neural network, and I am just little bit mimicking it to the vector representation. And of course, these are the basically parameters you have. So, weight parameter, you can say theta 1 matrix here and theta 2 here. So, just I am just redefining in a vector form. So, this is a vector, you have a multiplication operator here, theta is also a vector, this is theta 1, this is for the first layer parameter. So, every weight is a parameter here, so you can represent as a matrix. So, it is a 2 cross P matrix, right. So, theta is a, so you have a 2 cross this number of neurons that you have a P matrix. So, every neuron has a bias, by the way, you can call it, this is P11, this is the bias for this one is B21, right. So, second neuron bias. So, likewise for this one you have a bias BP. So, every neuron has a bias. Is it clear? So, just see here. So, we have this multiplication. Then you know that W transpose xi plus b. So, theta transpose xi. So, theta xi will compute here. You add with the bias vector. So, whatever you are getting from here, you just add with the bias. This is the bias of the first layer. So, this becomes a vector of p elements, right. For every unit you have one bias. So, just I am representing in the vector form. You have computed up to this part, so output you will get here. So, maybe some nonlinear activation you might have here. So, that activation I am just writing with a let some function f. So, this activation. So, pass this through some function f. Whatever output you are getting from here, right, activation output that you are getting, you have to multiply with this theta 2. You have a multiplication operator here. This is also a vector you are getting here. So, this is also a vector. So, you will get always, if you compute the gradient later on, you can say that you might get Jacobian net item. So, okay, is it clear? Then you have to add the bias here. So, this unit also has bias, you can say B1 for the second layer, to the bias here. So, this is B1 for the second layer. We have computed this yi cap. So, we are till this point, just put the minus here. So, this is yi cap, right. Then you have this, compute the square of the input that is coming here, and this we call yes. Here you have another input, that is the ground truth yi. Is it clear? So, this computation graph is clear to everyone. And this is, by the way, xi I am just writing here. So, this is xi. So, this is complete. So, most of the components are vectors. So, xi is a vector, theta 1 is a vector, b1 is a vector, whatever output you are getting is a vector. So, theta 2 is a vector, v2 is a vector, and then this yi that you are getting, so it might be a scalar. This yi is a scalar here. We are subtracting these two, squaring it, we are getting the loss. It is clear. So, can you compute the gradient? So, gradient of this loss with respect to theta 2, b2, b1, theta 1 or even xi. Can you compute? What is that value? Can you just tell me? Quickly, just do it. This is, you know, right. So, it's gradient of L equal to 1. This is a square. So, what does it mean? Let first, I am just writing this as G1, let timing, let this is P1, whatever you say that, maybe I can just write very simple, A, B, C, D, E, F, G, okay, do not worry. Just write ABCD because we have many nodes here. So let temporary value we want to write here. So let this is A, this is B, this is C, you are getting, this is D, right? This is already written, so let this is E, and this is already there. So what is this? So if so this means that you will L equal to E square, right? You have a square operator. So what is the local gradient? So what is the gradient of x square with respect to x? 2x, right? So twice of the input. So it is 2 into E, right? What is this? If it is yi cap minus yi, then you know that with this argument it is 1, and with this argument it is minus 1. That you know. What about this? So you are adding addition operator plus 1 with respect to this 1. What about this? This is exchange operator for this. This is theta 2. With respect to this, this is f. Right. What about this? This depend on the activation function. If it is sigmoid, then it is let this f is sigmoid. Let this f is sigmoid. Right. Sigmoid you can say. We have discussed in the previous slide. So this is f in what is the input? So the what is the output? F of this, right? So can f into 1 minus f, right? So f of this b, right? You can say, because output you are getting f of b, right? So it's same as the function itself. What is this? 1, right? What is here? 1. What is here? Theta 1. What is here? xi. Can you compute the gradient with respect to let b1 2, right? So can you compute the gradient of this loss with respect to this one? Maybe little broader. So this is the path we are following. Just see. So whatever comes at the path, you just multiply. So just 1 into 2 into e into 1 into 1. So gradient of this loss with respect to B2 is 1 into 2e into 1 to 1. So it is 2e. And what is e? yi cap minus yi. You just do it. What with respect to theta 2? Theta, the parameter at the second layer, you can say. What path we will follow? Follow 1 into 2e into 1 into 1 into f. F will multiply. What will happen if you compute with respect to B1? Just multiply 1 into 2e into 1 into 1 into theta 2 into f into 1 minus f, right, into 1. Is it clear? And what about with respect to this? Into xi. So you have nicely computed the gradient with this neural network. You might have many layers, it doesn't matter, right? Just only the thing is that whatever operator you are doing here, so here it is dense layer, so every input is connected with every neuron here, or you can say previous layer outputs are connecting to the current layer neurons. So this is dense layer. It might be sparse, right? It might be you might have different arrangement. Might be you say that okay, this is connected only to these two. This is connected to only a few part of this one, few part of this one. You just design that operator. Here we say that everyone is connected with everyone, so that's why we have a just multiplication operator. Dot product you can directly do here. Theta transpose xi you can directly do here. But it might not be a simple multiplication operator, it might be convolution operator. You just know that what is the gradient of convolution operator, just convolution operator. You have two variables x and y, you are convolving it, so what will the output? So, if your f is simply x convolve y, so you should know the gradient of this. So, you should know gradient of with respect to x and gradient of this with respect to just y. Use this as a operator, right? So, one node in the computation graph, you just do it. You can compute the gradient for CNN, convolutional neural network. The similar story is true for recurrent neural network. Right. So, whole neural network, any kind of directed acyclic graph that you have here. So, this is directed acyclic graph, there is no cycle. If there is a cycle, then there is a problem. You have to unfold the cycle. For example, recurrent neural network, we try to unfold the cycle, recursion, and then we compute the gradient. So, any network, if you are able to represent the computation as a directed acyclic graph, you can compute the gradient very easily. And by the way, this is a chain rule. If you write it, everything, every component here, multiply it, you will see that this is a chain rule. Okay. So, now neural network is done. Now, you know that how can you compute the gradient, how can you train it. Gradient descent optimization algorithm, you know, you have to only compute gradients and other things, you know. So, any deep learning model starting from the perceptron, same simple model, you can compute the gradient with transformer models that ChatGPT and BARD and Gemini, right, DeepSeek are using. Very easily you can do it. Okay. So, we are stopping here and we will discuss in the next session. Right. Okay, so thoda se math hua hai, right, but don't worry. Are you able to understand, right? And one thing, can you see here, one important point I want to tell you. So, when we compute the gradient in the backward pass, we are multiplying the things. So, even if you have many layers, so this is two layer we have, right? So, you have two multiplication here. Can you see here? Here and here. So, we are multiplying matrices at two places, right? Huge matrices. Because you have a theta 1 and theta 2, so you are multiplying, so theta's matrices. So, if you have many layers, so as many layers you have, those many basically vector, basically multiplication operation you have to perform. You have 100 layers, 100 multiplication will be there. So, if you have sigmoid activation unit, then you know that vanishing gradient will be a very common phenomenon. So, maybe your gradient will flow up to this point, let up to this point gradient flows, but because of this activation unit, let values become very small. So, when you just come here and you just, because f is in the multiplication right now on the path, right, fb into 1 minus fb. So, it will reduce the value, it might have a very small value. Let if it is near 0. So, the computation after this, the value, the significance, or you can say the contribution becomes very small. So, learning will happen up to this point only, and for the rest of them, learning stops. That is the vanishing gradient problem. Okay. So, how can you avoid it? You just sort the connections. So, that is called residual network. So, you just say that every alternate step, or you can say every after two step, you just sort the connections. You just send this input to here. You say that, okay, we know that here the problem is coming, so you just do the connection, sort it. So, you say that, okay, this input we are just sorting here. So, here also this input is acting here. So, in backward pass it will help us when we do compute the gradient. So, gradient will not be abruptly 0, it will not vanish. So, these are the temporary remedial solutions. So, ResNet architecture that you have already available in deep learning models, follow this philosophy, right. So, we are stopping here and we will meet in the next session for some puzzles and demonstrations, right.